Still, most convenient location. Let's start here. But I will be hiding the spice of But are you sure it's not like this?
That's fine.
Yeah.
Okay, so welcome everyone. Thanks for turning up during this very short notice. So Léonard was supposed to give the talk on Wednesday, but because of the flight, I think we didn't manage to uh, get the connecting flight and came all the way from Austria to Mumbai to give this talk. And we thought we should certainly have the talk here. And unfortunately, because of the airlines, we are also not going to have the tea and the snacks today. So which he will arrange when he takes the airlines maybe next time, right? So, uh, so it's a pleasure to have Léonard. Léonard works primarily in games on graphs, and he has also wider interests in theoretical computer science. And so he has looked during his PhD at various kinds of equilibrium with respect to multiple players. And particularly, he's very well known for his work on subgame perfect equilibrium with mean pair objectives, which won him a Conquer Best Paper Award in 2021, if I remember. And today he's going to talk about some other kind of equilibria, which is a more recent work. Yeah, please.
Thank you very much for this nice presentation. So hello everyone. I'm very happy that I'm finally here. It was not easy, but yeah, good to be here. So yes, I'm Léonard. This is me. And I'm going to tell you about some work that we've done with Tejaswini and Tom Hensinger. Those are those people. So these are our affiliations. I'm still officially a PhD student in the Université libre de Bruxelles in Brussels. And Tejaswini and Tom work at IST Austria.
You graduated, right?
I graduated, yes, but I'm still employed by this. But those are theoretical affiliations, let's say, because in practice, I'm starting a postdoc here and I'm physically there already. And since Tejaswini is tired of working with me, she's actually running away there. But yeah, those are our affiliation and you can consider them as yeah. Okay, anyway, so I'm going to tell you about this paper that we wrote, Finding Equilibria Simpler for Pessimists, Simplest for Optimists, which has been published in an FTS of this year. This title, sorry for the title, it's not very explicit, but we made actually the entire lab vote on it, but in the end, yeah, people didn't know about the topic of the paper anyway. So it's a paper about extremely sensitive equilibrium in stochastic games, if you want something a bit more explicit, but I will explain what I mean by that. So maybe let's first just introduce the model. What do I call stochastic games in this case? So usually when we talk about games in computer science, it would be to model such kind of situation, right? You have like typically one computer control system, like an online selling platform in this case, and you will have a human user. Or an environment in general, and you want to model to program your system in such a way that gives some guarantee what the environment is doing or something like that, right? Things become a bit more complicated whenever you want to design collective behaviors that imply that involve more than two agents. For example, if you also have a bank involved, and the bank doesn't want to be hacked either. And in such situations, when we want to prescribe a collective behavior that offers some guarantee, we will use the framework of multiplayer games, right? So typically for us, a multiplayer game will look like that. So it could be a multiplayer stochastic game in this case. It's a graph. The vertices are controlled by different players. So in this case, you can have 3 players, player circle, player square, and player diamond. It might be a bit rude in real life to call people by their shapes, but in game theory, you can do it. And you also have stochastic nodes in our games like this one. So just a probability distribution on the edges, right? And you can think of a play in such a game as a sequence of moves of a token along the graph, right? So when it's on the stochastic vertex, which is also the initial vertex here, it just moves according to the probability distribution. But then when it goes to a vertex that is controlled by player circle, in this case, player circle chooses where it moves next.
So,
Yes.
the start node, the S, which you call the stochastic node,
Yes.
so that's not owned by any player.
No, yeah, it's just you toss a coin and the.
That's the stochastic event that happens.
Yeah.
That's like the environment or something.
Yeah, you can think of it like that. No player has any influence.
Okay.
And one player can own multiple vertices also. Right?
Yes.
And there can be multiple circles.
It's not the case here, but yeah, as in this one. And you can have as many players as you want. Okay, so when it's on B, for example, of course, it's player square, then that chooses where it moves next. Oops. And yeah, you have those terminal vertices that give you like a payoff profile that tells you which player is going to get what payoff. So it's highly non-zero sum in our case, right? So you also have those terminal vertices here. And if ever you have an infinite play that never reaches a terminal vertex, then we just consider that every payoff is zero in this case, right? Even though you will agree that in this game it seems a bit unlikely.
Sorry, but how does I mean, from A, that's owned by player A, how does one move to the next node? Like, so player A makes a choice.
Yeah.
Yes, player circle makes a choice between going to T1 or going to B.
T1 is a leave node, like you don't come back.
Yes. Once you get there, like it's a finite play. Once you're there, it's the game is up.
So in this situation, so it's a little, this game, for example, looks like a little unfair for other players, right? Because the thing moves, if at all it moves to the player A, and then player A can decide to terminate the game.
Exactly.
Without player B and C even getting a chance.
If player circle chooses to terminate the game at this moment, the other players are not playing at all. So Square might be kind of happy with that because he will get the payoff 1, which is not that bad. He could get the payoff 2 in T3, but it seems a bit unlikely. But Diamond will not. But yeah, and what we are going to talk about equilibria. So equilibria, you can think of them as a contract between the players also. So, but of course, Circle has some specific power here by the fact that she plays first. Okay. So yeah, as I just said, in those games we're interested usually in collective behaviors that offer some stability properties, and typically those are what we call equilibria, and the most common one is the Nash equilibrium. So a strategy profile, one strategy for each player, will be called the Nash equilibrium if no player can just deviate unilaterally from their strategy profile and improve strictly their payoff, or in this setting, their expected payoff, because the payoff is of course not very well defined. So maybe we can just give a try. In this game in particular, do you see a Nash equilibrium in which the diamond gets the expected payoff 1? Can help you a bit with the beginning, maybe. So if you want player diamond to get the payoff 1, you have to go to C, right? Because in T1, she gets the payoff 0. But then you have a small problem, which is that if that player diamond goes up, then diamond gets 1, but square gets 0, right? And so in this case, square would have a profitable deviation by going here. So this cannot be a Nash equilibrium. And you have the same problem if you go down, because then player circle gets the P of 0, so she would have a profitable deviation by going to T1 as well. But
You have to pick on the randomization.
exactly, yeah. If you randomize half-half, then both players have the expected payoff 1, so going to T1 is no longer a profitable deviation. So this is actually a Nash equilibrium.
Oh, oh, if player C was playing half-half, then
Yes, yeah. So player C is kind of the referee here. She's the one that is going to guarantee the fact that the two players will get 1 and 1. But she's actually somewhat interested in that because that's That's what guarantees that the players will accept to go to C instead of going to C1, right? Which is what she wants.
Are all the players aware of all the payoff nodes? So he is aware of 2 and 3.
Yes, it's complete information. Yeah.
So this is sort of a mixed equilibria, right?
Yes.
So and there is this very well celebrated result that if some certain conditions are met, then you always have a mixed Nash equilibria, right? I mean, there always exists a mixed Nash equilibria. But this is not
yes.
true here.
So it's actually true here. I don't know whether it applies. So from the theorem in normal from games, you have that. I think that directly implies that there are such equilibria. Yeah, if I'm not mistaken.
So strategy would be the next mass strategy would be like the probability distribution over paths from this S to the means.
Sorry.
So like the one way of thinking about this mixed math, like strategy profile of mixed Nash equilibria, would it be like distribution over paths from the first vertex to terminals?
So okay, it's true that I didn't give the formalism for strategy profile. It's just a table of strategies, right? One strategy for each player, and a strategy. Oops, sorry. Formally, it's mapping that takes history and that returns probability distribution over the edges that you can take after that history.
I think his question is about like this existence of the mixed Nash equilibrium.
Yeah.
So how will you look at the strategy here? So he's saying that if you look at that as an that as this I mean the strategy you can think of like it's the entire path and the randomization over the entire path for each of the players. And that kind of sort of like is what he was saying that like mixed Nash equilibrium always exists.
No, but I think the strategy, as I said, it's basically a strategy is an action that a mapping that a particular player, the strategy for a player would be a mapping of a player given the history.
Given the history.
So therefore, as he said, it's a distribution over edges. Yeah, that that a player does given a history.
But you can see that as just you could also see that as a distribution over all possible deterministic strategies, right?
Yeah.
It's also a way to think of it.
Yeah.
It's a bit less intuitive move.
But it won't be over paths, right? Because the paths, because I don't think the path thing is correct.
Human box.
Maybe I mean, because of the history was given the history.
Yeah, because I mean strategy only talks about a strategy of a particular player, right? Not all paths are controlled by a player. So strategy would just be a distribution over deterministic strategy, but a deterministic strategy is just an action.
Yes. Right. Given the history.
Given the history.
But when you have all the strategies, of course, it directly generates a distribution of the place. You had a question?
Yeah, maybe you said this, but does it depend on the history or just the current knowledge?
The strategy depends on the history. Yeah, in general, we assume that.
Does it need to depend on the history though?
No, for the existence of Nash equilibria, there is actually a result that says that there is always a nevertheless one. But you can do more things in terms of if you have like such a constraint, if you want some player to have payoff one or something, then you might look to level.
So actually, so here you're making some assumptions also, right? Some sort of Markov or no, because the strategies could also depend on the. I mean, so does the player, let's say player A, does player A know about the strategy of player B?
Yes. When we talk about, I mean, implicitly yes, because in a Nash equilibrium, the question is whether the players have a profitable deviation considering the strategies that the other ones are following. So that assumes that they know it, yes.
Actually, there is a difference. And so the result that Nash says is like the game is simultaneously played. I mean, it's kind of like it's so there are two types of game. One is this simultaneous game, and one is this is I think called extensive form game. So like chess. So one player plays, then the second player plays. So in that cases, the Nash theorem does not work actually. So I don't actually. So that would be interesting.
You
if
could
there-
draw a connection between the two because you can always put an extensive form games in a strategy. You can always see that as just one
yeah,
game,
okay.
but with infinitely many possibilities.
Yeah, that's what I'm saying. But then the Nash theorem does not work because it should be compact
yeah.
or something like that.
Isn't that a question of the Nash?
But I think this should be a special case, right? They're not.
I mean, if your strategy set is infinite,
Right.
I'm not sure how would you define a distribution over that, and also like how the Nash theorem will
I
work.
think it still works, but we would have to check that. Anyway, there are more powerful results that say that, for example, the memoryless Nash theorem system.
Okay.
But yeah, anyway, we'll talk about another version of equilibrium, so maybe I can. So okay, that would be the big, the typical question that we would like to ask about Nash equilibria in such games, right? Like if you're given a game, if you're given lower and upper bounds on the payoffs of the different players, does there exist Nash equilibrium in the given game that generates expected payoffs that lie between the specified bounds, right? So this is what we call the constraint existence problem of Nash equilibria. And this is what we started to study actually with Tom and Tejasumi at first. And we worked on it quite a while before noticing that someone had already worked on it and put that it was undecidable. Oops. So we had actually missed that, and it's like very undecidable. Like there are actually several undecidability results. Typically, like if you don't have a stochastic games, but the players are allowed to randomize, or the contrary, only one of those two sources of randomness is enough to have undecidability.
Sorry, could you repeat that? Like, could you say what did you say? Like, what are the restrictions you're saying?
If the game is not stochastic, but the players are still allowed to randomize, or the contrary, if the game is stochastic, but the players have to play pure strategies, in both cases it's still undecidable.
And if the game is not stochastic, it means there are no such stochastic nodes.
Yeah, if there is no stochastic node, it's still undecidable.
But if there's like one stochastic node somewhere, already you consider that.
If there's just one, I don't know. Maybe not. Maybe you can find.
So, but then there has to be an adequate definition of what you mean by a stochastic case, right?
Yeah, I mean it's the general problem, right? Like if you're given a game that lies in this general class in which you can have stochastic nodes, then it's undecidable. If you take a subclass of those in which you can have stochastic nodes for just one or two, then I don't think that case has been studied.
I mean, it may depend on how the undecidability has been encoded and how many.
Yes,
No,
yeah, sure.
no, like, is it like every path you encounter a stochastic node somewhere? Is that what is called a stochastic game?
No, not necessarily. It's just you have some stochastic nodes.
Then I don't understand.
Okay. So at that moment, I'm in Austria and I have to justify my presence there by something else than nice landscapes and Affiliation. So we had to come up with a new problem. And
So, by the say, if this is like some trivial bound somewhere, like if I say the expected value is just greater than xi or less than yi, not both the bounds I'm giving, but in that case, also,
I think that doesn't change much because you could encode
like one
such a
is
constraint
just
just
zero
by.
or something arbitrary. I mean, something trivial. Like if
So if it's completely trivial because like there is
expected
no bound basically, then it becomes decidable because they are guaranteed to exist. But as soon as it's just one player, I think you can just put a gadget at the beginning of the game to encode the rest of the constraints.
So if you have only one bound, you can do binary search, right? To find a lower bound also, like so if you can do it if you can decide for just upper bound, you just do it for yy2, yy4, and wherever it breaks, and then you have a lower bound there.
I mean, you have some kind of a granular.
I'm saying that,
yeah.
okay. I don't think it should change much.
So okay, so we have to question a bit the problem and to look for something else that would also be relevant, especially in the context that we usually face. And what we choose to challenge is this. The general notion of Nash equilibrium in stochastic games is always defined considering that every player tries to maximize their expected payoff. But that might be quite questionable in practice, right? What would the expected payoff be in all cases? How you perceive the payoff that you will actually get, right? If you think of these kind of situations, the bank and the online selling platform could be agents that want to that don't really care about expected payoff. They don't want like probability 1/2 of being hacked is not something that will satisfy them, right? What they will more reason about would be like the worst case scenario. There are some guarantees that they absolutely want to have, right? Or at least with probability 1, which practice is something you're quite sure about. So they don't have that tolerance to risk, is the notion that is the word that I should have pronounced. And so different agents in real life will have different perception of risk. So that's the notion that is usually captured with the notion of risk measure. What is a risk measure? It's just a function that takes a random variable with real values and that returns a new random variable. So typically the expectation is a risk measure, but you can think of thousands of them. And yeah, in finance and those fields like that, there are many people that have thought of a lot of possible examples of risk measures that could be relevant in some contexts. So the question would be,
Sorry, put it
yes,
back. I think. So okay.
So this is a very general notion. We'll see specific.
So what is this thing you're saying? Example, the expectation. What do you mean by that?
The expectation, expected payoff, is a risk measure.
Okay.
It takes a random variable with real values and it returns. So you could, yeah, a risk measure is just a generalization of the expectation. So if you have a given notion of risk measure, that's it will like encode how the perception of risk that player will have typically. You can define a notion of risk-sensitive equilibria, in which you can assume that every player has their own risk measure, which their perception of probabilities in general. And you can define a notion of risk-sensitive equilibrium by saying that each player wants just to maximize their own risk measure of their payoff, right? So no player must have a profitable deviation, a deviation that increase their risk measure of their payoff. So if, of course, you take the expectation as the risk measure of every player, you find back the definition of a Nash equilibrium. So you can think of it as just a generalization of the Nash equilibrium, right? Okay, so now the question.
So in general, now
yes.
you're saying that players may be having different risk measures, right?
Yes, they can all have different risk measures. So now the question would be, which type of risk measures would be interesting for us in computer science? And usually in computer science, as I mentioned before, we like to study worst case scenarios. So this would be a very simple risk measure, the pessimistic risk measure. You can define it as just, okay, so this is the actual definition, but when you have finitely many values, which will be the case of payoffs in our case, you can think of it as just the minimal payoff that, or the minimum value that a random variable can take with positive probability, the minimal payoff that you can get with positive probability. So you're just extremely pessimistic. You don't care about the other payoffs. You just consider the least one that might occur even with very small probability, right? This is the pessimistic risk measure. And we like worst case scenarios, but we also like duals. So we would also define the optimistic risk measures in the way that you can imagine, I guess, the best payoff that you can get with positive probability, right? And so from this point, we will assume that when we're given a game, we are also given a partition of the players between pessimistic players and optimistic players. So when you have such partitions, so here, P would be the set of pessimistic players or the set of optimistic players. You can group those two risk measures under the umbrella term of extreme risk measures, because we take the extreme cases, right? And consider that the extreme risk measure of the pessimist will be the pessimistic risk measure, and same for the optimist. And now we can define the notion of extreme risk sensitivity equilibria, which was in my, so which is actually the notion that we're interested in.
In general, some players may also be interested in the expected measure. Right?
Of course, yeah.
But that's not included in your pessimistic and the optimistic only.
Yes. Now we'll just focus on pessimists and optimists, because the expected payoff also has a big problem. It's not only that it's not always relevant, it's also that the problems with Nash equilibria are undecidable, right? So those are our two objectives. We are looking for something that is relevant in the context of computer science, but that is also tractable somehow. But maybe I'm a bit slowly passive when I said that. But okay, extreme resistance equilibrium, you have optimists, you have pessimists. No pessimist should be able to deviate and improve the worst case scenario. No optimist should be able to deviate and improve the best case scenario. Okay? Okay, let's go back to this example. What would be an extreme risk sensitive equilibrium, XREC, in this game? So I can present you, so yes, let's assume that circle is pessimist here, square is optimist, and diamond is optimist. It's a completely arbitrary partition, right? And let's show one XREC here. Oops. Yes, this one. So circle is going deterministically to B, then square is randomizing between the two, and then if C is reached, diamond is going to D2. So what would be the extreme risk measure of circle's payoff here?
One.
Yes, circle is pessimist, so she can get either 1 or 2, so she just considered that she gets 1. Okay, square. 1, yes. Square is optimist, so he can get either 0 or 1, so he considers he gets 1. And well, exactly the same for okay. Okay, so so this is an extreme sensitive equilibrium that has exactly the same payoffs, extreme risk measures in this case, that the one that I showed in the beginning, right? 1 for everyone. Okay, so now you have the example. First result, those equilibria exist, at least if you have non-negative rewards. Our proof only works in this case. We conjecture that it's still true if you have negative rewards as well. But yeah, if there is any volunteer to write the proof, it's already quite long.
Another question, so aren't the partitions like always like say contain at least one there?
No, not necessarily. You can have all pessimists or all optimists. It's also a useful case.
So what breaks if you just look at a sum, if there are negative rates, and if you add the minimum value to everything, make it negative.
So it's because when you don't reach a terminal, it's 0 for everyone. So if you have negative rewards, it means that you could have a profitable deviation by not reaching a terminal. And like, okay, actually, it might not be that more complicated. The thing is, we noticed like 1 week before the deadline that our proof that we had failed because of that case. And so we didn't really analyze it. We just said, okay, we have only positive rewards, it's too late. And we did not really get back on it. But yeah, like, and other proofs that work in all general cases, basically, we are fighting all the time with this specific case of deviation that's implying not reaching a terminal. Yeah.
For these definitions, do the probabilities even matter? The only thing that matters.
No, that's a very good point. What matters is what is done with positive probability, but from now on, the players can just randomize between two things, and you don't really care about the probabilities. It could be 1 by 10 and 9 by 10 or 1/2. It's equivalent. Okay. So now the second question is this one, constraint existence problem. Actually, for that reason, somehow it's a first intuition. And now something that was like very continuous, the Nash equilibria with the expected payoffs, is becoming more of a combinatorial object, right? Which is what is bringing something more tractable. And so actually the constraint existence problem is now decidable with this case, and it's even empty complete.
So you mean the probabilities of the on the randomization in the algorithm?
Yeah, the only thing that matters is the support. Doesn't matter what the number though.
Yeah.
Is this a case of having a half-half probability is kind of like taking a non-determinate choice? Is that how the NP this is rigged up?
It's no, that's, you can think of it like that. Yeah, the players are just deciding what is possible and what is not. So it's a strategy becomes a non-deterministic strategy in some sense more than a probabilistic object. Yeah. But I will give more intuition on that. So, but just on this result, let's say that it's also true if you restrict the players to pure strategies, to stationary strategies, and to positional strategies. Positional both for pure and stationary, sorry. And what's the idea? The idea is that you need only finite memory for such an equilibrium to exist. So let's show why, but let's do that through some more examples. Here we have a game that is quite simple, only two states, only two players, and the two players are assumed to be pessimistic. So you don't necessarily have an optimist in the game. And I'm asking you the question, in this game, does there exist an XRC such that the two players get extreme risk measures, pessimistic risk measure, worst case scenario, 1? Does anyone have an idea?
If you press half everywhere, does it work?
Half everywhere. So
Press half everywhere.
so that's a good start. That the idea is that you need to reach both T1 and T2 with probability not zero, right? So at some point you need to randomize between the two. So you need to have something like that. So it's not exactly half everywhere, but it would also have the same consequences, right? Because yeah, you want the worst case scenario of both players to be 1. But that implies having at least one of the players that is at some point randomizing between the two options, right? And somehow like tossing a coin to decide which player is going to get 1, which player is going to get 2.
Yeah.
But there is a problem here because the player that is doing that randomization is very interested in the outcome of the different. I don't know what's the stuff. But okay, so yeah, so and the thing is that player is just randomizing, but it's like an internal process, the randomization. So the player could just lie about the outcome of this coin tossing, right? Because the other player doesn't see it. So here, circle could just deviate by never going to C1 and going to B, and square will not even notice that it's a deviation because he will think that it's just the result, the natural outcome of the randomization, right? And this would be a profitable deviation then, because circle just.
I didn't understand. What do you mean? You said it's a full information game, right?
It's a full information game, but when the player is randomizing, the randomization, the other player cannot see whether you randomized fairly with regards to what you've announced. Because like in
But in a full information game, I thought you know the probabilities of the probability that a particular player assigns on a strategy is known to the other player, right?
you know in the Nash equilibrium, you know, because the Nash equilibrium is like a contract between the players, but you cannot check that the player randomized fairly with regards to what was announced in that contract. Because a strategy of a player is just a function that takes a history and that returns a new distribution. So here the history is the same if the player has randomized, if circle has randomized fairly, or if circle has deterministic to be.
No, but a particular strategy will say whether you are randomizing or you are choosing a deterministic strategy, right? I mean,
yeah.
So what is the strategy here? You are.
So here the strategy of circle in the Nash equilibrium itself, which is not an equilibrium, sorry. In the strategy profile itself, is after the history A, single state history A, circle is randomizing between the two. You don't really care about the probabilities, right? And after the history A, B, square is going deterministically to T2. Okay. And after the other history, it doesn't matter because
Why is there going to demonstrate between T2?
That is the strategy of.
That is just one example of a strategy, right?
So let me understand this correctly. So if the player just player A does this, so it has two edges, and let's say it chooses one of the edges, both of the edges with half probability.
Yeah.
Then the best response for player B is just always take that surface. that loop back, right?
Yes,
But best response, we don't really care about best response.
So I'm saying that B is just playing that age back to A just with probability 1, isn't it?
So that would be a punishment. There are punishments that's true. If you want to, if you don't want that deviation to happen, you can punish it by doing that.
Yeah.
But the problem here is that you will not detect the deviation. It's an undetectable deviation in the sense that it's just about changing your probability distribution, but you're still doing something that might have happened if you had not deviated. So for that reason, you cannot know like the what Square has just planned to do something after the history AB, and the history AB is happening, so Square is doing what it's supposed to do. In the history, you don't have the internal process of randomizing. You just see the vertices that have been visited, and that's it.
So there's one thing I'm not quite understanding. So B is an optimist, right?
No, he's a pessimist. Yeah.
No, suppose we change the
Okay.
assignments, right? Let's say B is an optimist and A is a pessimist. So
Yeah.
A is also an optimist, let's say.
Learns.
So in that case, so because we are allowed to have like equilibria and B.
Yeah.
So in that case, would this not result in an infinite loop? Like no matter.
So if the players are optimists, it's very different because like if they're randomized, they will get the best case scenario, which should be that they don't have a professional deviation anyway. Best case. Optimists are in general very
Can you repeat that?
optimists are in general very happy with randomizing between the other option because they should be able to consider that they will get the best case. So in this case, if they're randomizing like that, but they're optimists, they will just both have two and they will not have.
So I don't understand something, sorry. I mean, yeah, so are you saying, so depending on a history, let's talk about circle, player A. Your player A has a certain strategy, which basically is a mapping given a history what the player A will do.
Yeah.
I mean, it could be a distribution.
Yes.
Now this distribution, for every history, the distribution that player A has,
Yes.
is it known to player B or not?
It's known. Yes.
So then how can you fool? How can you, I don't understand. What do you mean by the fooling thing?
Basically,
Uh,
distribution is known, but given a realization, you don't know whether they are following that or not.
yes.
But there's a contract, like there's a.
So then I don't say it's known. So you're saying,
Yeah.
okay, so they announce something.
Yes. But you don't know whether they are actually.
Confirm this now. Otherwise, I'm not having full information. Yeah.
Sort of, yeah. There is some kind of.
Completely, I was getting.
So
Okay.
they change their strategy on the.
So these are not.
No, these are like public profiles.
Yeah, they
That
are.
is there, but they're.
Yeah.
So then fairly doesn't know. So like,
Yes.
you're saying there is an announced knowledge, but player A is free to deviate from that.
Exactly, yeah. When I
So
say.
then it's not a full information.
Yeah.
Why would I then know? I mean, what is the guarantee?
Like, for information should mean that,
Yeah. What I mean with full information in this context is just that you, or every player always knows in which vertex you are.
That's
And,
what I meant by, okay.
and yeah, okay.
So
so-
I'm saying that I don't know the strategy of the other.
But you don't know the strategy of the other player, but you know what the initial contract is supposed to be. So you know what they are supposed to follow, but you cannot check that.
So there's no value of knowing what they're supposed to follow if the supposition is of no use.
Well, that's not, no, if you have the support of their strategies and they deviate by doing something that's not even in their support, then you cut them, right?
No, so then, okay, so you're saying the probabilities can be fudged, but the support of the non-zero distribution is fixed. Is that what he has to confirm that? I think what Ian was saying, that the support at every stage,
Yes.
the support, by support I mean the support of the strategy.
Mhm.
Yeah, so the set of things that A can do,
Yes.
that is not deviated. With what probability will A take those? Those might be.
No, you can deviate from that if. But you can deviate from. You can change.
But then nothing is known.
No, the
Why
thing
would I
is-
assume that anything is known? I know nothing about player A.
for it to be an equilibrium, you want it to be resilient against deviations of one player. So if everyone can deviate, then you don't know anything.
At equilibrium, you observe a player and say that, okay, this is what the player A is doing. Assuming that the player A is doing this, I will not change. I understand that.
Yeah.
But you know, when you are playing the game, you at this point you don't know what player B doesn't know what player A will do.
Player B doesn't know what player A will do. Yeah. That's the idea, but
Then you don't know the strategy of player A.
Yeah.
Player B doesn't know the strategy of player A.
Player B is playing in such a way that if player A is following the strategy that she's supposed to follow, then everything goes well. And so he's supposed to guarantee that if player A is following that strategy, everything goes well. And as soon as player A deviates, then that deviation is punished. That's how you should think of
Then you did something outside your strategies.
No, I understand. But what is the punishment? How is punishing? What is the mechanism of punishment?
Maybe the next example will make it clear.
Okay.
Yeah, and then we can come back to this one.
But you should define things before. I mean, otherwise,
Okay.
I'm being punished.
So, maybe we can have this. So if strategy profile would just be like, I can write it this way. Sorry. You have that this tuple of strategy is so this is the set of players is the one that the players are supposed to follow. And these strategies have to be designed in such a way that first, if everyone, if everyone is following this, then the constraints are satisfied. So the constraint is like the upper and the lower bounds x and y. So that is the first requirement. And the second requirement, which makes it an equilibrium or not, is that if just one player deviates and follow another strategy, sigma prime I, then this new strategy profile, in which only the player I has deviated, will be such that the payoff of player I, or the expected of the risk measure of that player, will be lower or equal to what they were supposed to be. So there is a punishment in the sense that there is a punishment that should be encoded in this strategy, in the sense that what is going to happen in this scenario should be bad in some way. But this punishment can in practice happen in several ways. Either you're like just preventing the deviation to happen by just securing something, or as soon as you go to a vertex in which you're not supposed to go, for example, then all the players are just playing something that is fully hostile, because then it doesn't impact what is happening. Yeah. And then that's what you could like really call a punishment. It's something that could happen in a subgame that is anyway not supposed to happen. So as soon as you're here, you know that the player deviated, so now you don't care about your own objective, you're just like, that's punishment. Which is what doesn't happen here, because when you get in B, it's still kind of regular because it's something that is supposed to happen. So if the player circle deviates discretely by just changing the probability distribution, player square will not notice it because it's still a normal history. It's not a history.
So you were saying that what player we can observe is the history and not the distribution.
Yes, exactly.
It can.
So that is why what is the support.
Yeah.
Yeah. So if actually a player A deviates in terms of the probabilities.
Mm-hmm.
Yeah.
But not in terms of yes.
Yeah, the strategy of player B is dependent on the history of.
No, I understand. But I'm saying
observed.
I mean, so there is an announced strategy.
Yeah.
And now if player A, let's say, deviates from that in terms of the probability of choosing a particular edge, that I mean, if it was, if both of the, if actually what he is doing and what was supposed to be done, if they both are non-zero probabilities, then it will go undetected.
Exactly. Yeah.
There won't be any punishment.
If you're making some probability zero where it was supposed to be non-zero, then that will go.
Right, but if you make something non-zero and it's supposed to be zero, that can go.
Yeah, that will definitely be detected, but it will be detected only when it happens.
But yeah.
The players won't know before that.
The definition of the strategies from history to the next.
So maybe next example, because then, so yeah, that's the idea. The players don't have a common coin to toss when they're doing those random experiments. So they agree on the contract of strategy, but they are not randomizing together. Every player is just randomizing on its own. So next example is this one. Now it's the same game, but you have a stochastic node at the beginning. And we are asking the same question. Does there exist an equilibrium here, an XRC, in which both players get pessimistic risk measure 1? So what do you think in this case?
Yes, the strategy would wait.
Just a straight
Yeah, I can just go down.
Yeah.
Yeah.
So now you can use the first stochastic node as a common coin, and it's the outcome of that random experiment that everyone can observe that will be used to decide which player is going to get 1 and which player is going to get 2. And now, if one of the players try to deviate from that, so let's say, for example, Circle, she doesn't want to get 1, she wants the 2, then this will be a detectable deviation because the history CAB is a history that is not supposed to happen. So when that happens, Square can play something else and just decide to stay here, and then no terminal will ever be reached. So for Circle, it's the payoff 0, so it's not a profitable deviation. Yeah. Does it make clear the rationale?
They're both punished, not just.
Yeah,
We also next point.
Yes, exactly. Well, since it's something that is not supposed to happen anyway, Square does not care anymore about use on payoff in this case. In the main play, what happens with applications, Square gets the worst case payoff 1, and he's happy with that.
So, like, just throwing it out there. So, what happens if the anti-strategies are also public? So, for example, so this is a very simple case. So, I'm not talking about this case. So, for example, you know that like if you deviate from the planned strategy, so then the other player is also not going to follow the strategy as planned, right? Because
He is. This
no, I mean, say for example, here like at A, now B knows that if C goes to A, then you're supposed to go straight down. This was the agreed upon strategy.
Yes,
Yes.
he knows that.
Now, if B suddenly sees that A is sending something to B, then A has clearly deviated from the agreed upon strategy, right?
Yeah.
So in that case, B always like B punishes A and themselves by going back to A.
Yeah.
In this case, like ensuring that A never profits. So this is let's say this is like an anti-strategy.
It's still part of the strategy.
It's still part of the strategy. So is this part also known beforehand?
Yes.
I see.
The players know all the full strategy of the player. So here the strategy of Square consists in after the history CB going down, after the history CAB going back to A. And that is for me. Okay.
So in the previous game, was there an XRC?
There was an XRC, but not one in which both players get 1. Yeah, what I gave as a strategy was just an example to explain that, but the argument can be generalized to every. As soon as there is a randomization between getting 1 and getting 2, the player is very interested in the outcome of that. So that's the reason why there is no such XRC in that. Okay, last one. It's still the same one with the stochastic node in the beginning, but between the stochastic node and the part with A and B, the players are facing some temptation. They are given the possibility to.
What is the XRC for that game?
So that's the question I'm asking you.
I mean, previous one or before the previous one?
For the previous. Okay, sorry. For the previous one.
No, the one before.
Before this, in this one you could have something in which there is just no randomization. Like you go deterministically to T1, that is an XRC. Because then if the circle deviates and goes to B, Square can
So that will give you 1.
That would give 1 to Circle and 2 to Square. Or you could also go deterministically to T2. Both work. It's the randomization that is not one.
So A goes to T1 and B goes to where?
C goes to T2.
No, these strategies
But
always
then
go
you
back.
can always move
Yeah.
and then you will get a better payoff, right? Then
Yeah.
circle can always go to like if both the strategies are going down, then it's not going to be.
No. The
That
equilibrium
will be
is-
an equilibrium. But I have this actually. If A goes to T1 always, and square always goes back to A, this is an equilibrium. Because that's the going back is the punishment if ever square circle deviates, right? Okay, but in this one now both circle and square have the possibility to deviate and go to T3 before reaching A and B. So do you think that there still is such an XRC in this case? Yeah, want to try?
I don't know if it works, but whoever it goes to, they send it down to their lower node and then send it across.
Exactly. Yeah. But you probably seen that talk actually, don't you?
I did, but it was like I don't know the examples.
Okay, that's the idea. If from C we first go to B, then only the player circle is given the possibility in this case to deviate and to go to D3 and to get the payoff 2, right? So you can actually do this and say, okay, but anyway, it doesn't matter because circle is going to get 2 in here. And we are in this case fixing, anchoring the payoff not of circle, but of square. And same in the other case.
But what if both of them choose to go to T3? Yeah.
That would be 2 deviations.
Sorry?
That
Yeah, both of so the strategy profile is like both of them are trying to go to T3.
this is also an XRC, but it doesn't satisfy this.
Oh, you mean you want one? Okay,
Yeah.
for both of them, I see.
So, for example, if circle deviates now and wants to get the payoff2 in this case, well, it's not really a profitable deviation because it doesn't change anything to the fact that there is still a play that happens with non-zero probability in which he gets the payoff 1. So, the worst case scenario is still 1. And actually, this is still true even if you change the payoffs in T3 with numbers that are so large that I'm not even sure they exist, such as 6. Even this is not a profitable deviation, right? Even though it's profitable in this specific play, the worst case scenario for circle is still 1, so it's not interesting. Okay, so this is the idea. Now we can think of it in something a bit more abstract. What is fundamentally a strategy profile? It's like a tree with all the randomization that may occur at some point. It can be a stochastic node as well, or it can be just a player randomizing. And if you have, let's say, a pessimist that gets risk measure Z, it means that there is at least one play, but there might be several, in which they get the payoff Z, right? If you want to deviate now, if you want to find a profitable deviation from that, it can be either just lying about the outcome of some pointer thing somewhere and just don't go somewhere, and that is an undetectable deviation. Or you could make a detectable deviation somewhere and just change and go somewhere where you cannot when you will just fight against all the other players but still get something that's better than Z. But as long as you still have one play in which you get the payoff Z, this is not a profitable deviation because you still have this worst case scenario. So if you want to build an XRC that will match your constraints, that is fundamentally what you need. You need to guarantee that there is at least one play that anchors the player's payoff. So it gives the player that payoff, and it's a play from which the player cannot deviate or cannot have a profitable deviation, cannot go somewhere where they can force more than that, right? And for that, you don't need a lot of memory. You just need to remember which player you are currently anchoring. And you need to remember if some player has deviated, because then you just switch to punishing. So you need memory, but you can bound it polynomially. And that's the idea to prove NP easiness of our problem, right? Okay. Polynomial solution, that's what I said. Now I haven't talked about optimists. What's the idea for an optimist? Well, now Z is your best case scenario, right? What is the profitable deviation for an optimist? Well, you just want to have a positive probability, something that is better than Z. So this is not happening anywhere in the tree, right? So there is only one type of deviation that can be profitable for an optimist. It's just leaving that tree somewhere. If there is some place from which you can force something that is better than Z with positive probability, that will be a profitable deviation, but that is always detectable, right? So optimists are actually kind of simpler to deal with, because if you want to build an XRSC with optimists, you just have to guarantee that you're never going at any moment with any positive probability to a place from which the player can force something that is better than them. So that is kind of the cherry on the cake. If all the players are optimists, actually the problem becomes even simpler. It becomes free-time complete. The NP hardness result that we have for the general problem is with only pessimists. So pessimists are like strictly harder to handle somehow than optimists. And it's so just I have just an example to give you the algorithm, but okay, I can do it quite quickly. If you have this game and you want to know whether there is an XRS in this game in which circle gets the best case payoff one, so we have only optimists here. How would you do? You would, so yeah, everyone's optimist. You would start by the profile that randomized between all the options. So actually, it's a bit subtle. You have to randomize, but when you come back to a vertex, you have to stick to the same place. That is just to guarantee that if you can cycle, okay, in this case it doesn't happen. But if there is a possibility of cycling, it's also considered one of the possible pairs, right? But okay, you're randomizing between all the terminals is what matters here. And then you identify terminals that do not match your constraints. So in this case, this one, you want circle to have best case payoff one, so you don't want to go there. Okay, you just remove this and you no longer randomize to here. But then you have a problem because square has a profitable deviation by using that edge, right? So from C, square can actually force best case payoff one instead of 0 that gets here. So you don't want to go to C because that would give square a profitable deviation. So you also remove you don't want to go to C, so you also remove this. And now you don't have any profitable deviation, so you can end the algorithm here. So it's basically just that removing edges and edges until you find something that satisfies your constraints, or until you can say that there is none. Okay? So the answer to the problem in this case is yes. Thank you. And if you want to discuss a bit more, I also work on those topics if someone wants to talk later in the day. I'm available. Thank you very much.
Okay, questions?
So again, just that, I mean, I asked this question earlier, but I think the way you laid out the trees kind of makes it clear, right? This follow time thing is because you only consider these deviations, detectable deviations, whereas the pessimists are allowed to, again, non-determinism, I guess is the right way to put it, right? Like the ability to just trim off these branches, for example. These randomized branches.
Yeah.
As they see fit.
Is
that how the reduction goes?
Not really, because in the reduction you actually have a game in which if there is an XRC that satisfies the constraint, there is a pure one. And in a pure strategy profile, you cannot have an indexable deviation, right? Because you're never repeating. It's more about the fact that so let's go back to the true one. Oops. So if I'm here, yes. Even so, you still have randomization in the sense that you have stochastic vertices, but that is right. No one can lie about the outcome of stochastic vertices. But it's more about the thing that you have to take care in all the branches that are not. Like if there is a profitable deviation, it's a profitable deviation in all the branches. And actually, something that I've quite hidden under the carpet here is that if only one play is not necessarily enough in practice, in the sense that if you have a stochastic vertex here, or if it's player I, so the pessimist here, who is randomizing here, you actually need to anchor his payoff on the two sides. So you may need several of those anchoring plays for that player. And I'm trying to think of the reduction now. It was a long time ago, actually. But I think that also plays an important role.
Okay, is the upper bound easy, the NP upper bound? Because you give us a p-space one on this slide, right?
A p-space one. No, it's NP complete.
Right, you've written polynomial memory sufficient, so, okay, it's in p-space. How is it in NP?
You can just you guess the strategy profile, and so the strategy profile is like a machine of polynomial time. You can guess it in polynomial time, and then checking it is not that hard.
Oh,
it's it's an Markov chain. Okay, it's a bit more than that, but it's not the hard part. And yeah, the lower bound.
And these are all memoryless strategies you do that.
So for the lower bound, we have so it's a game in which you never come back to the same vertex anyway. So it doesn't matter if you're restricting the players to memoryless strategies or not. It's NP hard in those two cases. So we have an NP complete result in the four cases actually. General case, only pure strategy, only memoryless strategies, and only polynomial strategies. All of this is the same. But you need stochastic nodes.
Sorry?
You need stochastic nodes
Oh,
for those lower bounds to.
okay.
So have you worked on the approximate equilibrium in the case of pessimistic? So pessimistic is like NP complete decide. What about approximate?
We haven't thought at all about approximation. That would be an interesting question, actually.
Sorry, what was the question?
So the question is that in the pessimistic case, there is no, there is equilibrium, but it's hard to decide an equilibrium. But in many cases in game theory, you can decide a approximate equilibrium very efficiently. So can you do it in the pessimistic case even?
I don't think it's that much the case in here because those equilibria are completely combinatorial objects. Especially in those games, so the set of expected payoffs that you could get in a Nash equilibrium or like continuous objects, right? But when you switch to this notion, the extreme risk measures that you couldn't get in the different equilibria that exist in the game are just discrete objects, right? They just correspond to the payoffs that you could actually get because you just focus on the worst case scenario. So I don't think any approximation based on a notion of epsilon XRSC or something would really help you because what does it mean to be an epsilon, like a deviation? When you have a profitable deviation, if you have a profit, it necessarily means that you have a jump, right? So yeah, I don't think it will help that much now. But we also have a paper about epsilon Nash equilibria and approximates the same problem for Nash equilibria approximated. We have proved that it was NP to the NP and representing that in FSTCS.
Okay.
So if you have epsilon even for the expectation thing, like if you then you can do such kind of binary search on either way, right? That seems to be.
No, but he's saying I'm talking about the pessimistic one, not the undecidable.
No, I'm just talking about that one. That
Undecidable.
I think epsilon, you cannot instead of some xy exactly to say epsilon close to x and epsilon close to y.
Undecidable, you cannot do even
approximately. I'm saying the other way around. I'm saying that with the binary search, you can do possibly, no?
No, I think because I don't know. I mean, if you have a pitas for that, or not pitas, like if you go, if the epsilon can be arbitrarily close to this 0, then you are basically, I don't know. The thing becomes like decidable, right? Because you can make the epsilon as small as possible. If your algorithm takes an epsilon and gives you this epsilon bounds, you can make the epsilon as small as possible.
But not exactly. Like in speech,
random.
Like that epsilon random. You cannot say exactly, but given any epsilon, I think the binary search might work.
Okay. The problem in this case is that if you let's say for example all the rewards are just integers, then when you have a deviation that is profitable, it's necessarily profitable by at least 1. So epsilon equilibria, you want to define the depth.
That's exactly.
Then if epsilon is smaller than 1, it's just the same as the equilibrium.
If the epsilon is smaller than the bit complexity of the input. That's it.
Yeah.
Thanks.
What other kind of risk measures have you like considered?
So I think I give a list of very
So the entropic stuff.
yeah, the entropic stuff it's also in our paper. We've quickly worked on it. So it's okay. I will try to remember the definition. So the entropic risk measure for like some eggs. It's an entropy for like those kind of formulas that are with a logarithm and an exponential, and you don't understand where it comes from, but in the end, it's has nice properties. I think it's that, if I'm not mistaken. So you have some parameter gamma that's yeah that encodes your sensitivity to risk. If it tends to 0, it will correspond to the expected payoff. If it tends to plus infinity, it will give you the pessimistic risk measure, and if it tends to minus infinity, it will give you the optimistic one. But it's more general than that. So we have a few results about that when we restrict the players to stationary strategies and so on. It's in the same paper. But it's also undecidable everything with that, of course, because just the case gamma equals 0 is the classical Nash equilibria, right? So it's a generalization of an undecidable.
Okay, so if there are no more questions, let's land. And we are happy that your objective for coming to Mumbai has become. So Leonard is here all day throughout today, and he has some very interesting results about this subgame perfect equilibrium and other things. So you know, talk to him. Yes, please.